Yeah, sure. Oh, what? All right, okay. So, okay, the title seems pretty nice and fascinating. I mean, we have helicopters, we have ballistic impacts, and then it comes the nerd part of physics informed and so on. But this is actually the first thing that might come to your mind, and this is my case. It happened in my case, especially during applying for the PhD position. But this is not the real case. Of course, we are not shooting any operating helicopter, and we are not using those massive guns to destroy them. Most realistic scenario would be this structure, which is located in Italy. It's an experimental full-scale test rig, and it's actually the half part of the helicopter, so it's only the tail boom. So from the whole transmission line of the helicopter, we have only the tail transmission system, which ends up to the tail rotor, which is located up there. And this is a representative structure of an Augusta Westland helicopter 139 and 189 if we change some components, some internal mechanical components, such as this oblique shaft. But it's basically a representative model of Augusta Westland helicopter. And with this experimental setup, we are able to perform various tests, dynamical tests, and acquire really nice data from many sensors mounted in this structure. How the system operates is basically there is an engine here, and it provides power to the transmission line. And then we can also control the pitch of the blades of the helicopter. So when we have an actual helicopter flying, we may see the internal mechanical parts of the tail, and it's actually the engine, the horizontal shaft here, which is in most cases around 3 meters, the intermediate gearbox, and then the oblique shaft, reaching the tail gearbox, and at the end, the tail rotor. So we are interested mostly in this oblique shaft over here, which will be experience ballistic impact occurrence. The size of the bullet, the diameter is 12.7 millimeters, which actually corresponds to a length like equal of a palm. So the length is like that big. And this is exactly the bullet we are going to use to impact the full-scale test rig I have showed before. Usually, every helicopter is equipped with a HAM system, which HAM stands for Health and Usage Monitoring System. And this system is responsible to obtain data and monitor various mechanical parts. And we save this data basically to be processed by aircraft maintenance and fleet operators in order to determine a better plan for the operation of helicopter and improve the maintenance plan, for example. But there is no specific tool for ballistic impact detection. So there is no such thing implemented in all the fleets of helicopters. And if we consider that this transmission path is the only way for the engine to transmit power to the tail rotor, and there is no redundant backup, it's really critical, because if it is, it will be solved, then the whole structural integrity of the system will be compromised, and of course the safety of the crew. So again, on top of that, if we consider the nature of the shaft, that it is exposed by nature, then it becomes even more critical. Implementing a system for ballistic impact monitoring will be an asset in terms of safety in this case. Okay. So typically, the rotating machinery, it's the structural health monitoring of rotating machinery is realized based on vibration. It's vibration based. So what we do is we process vibration signals and we try to extract some features in frequency, time domain, or perform order analysis and understand how the state of the structure has changed due to some specific reasons, due to damages, for example. So we perform parametric studies regarding the location and the ballistic impact severity, as well as some operational parameters such as the rotational speed or the thrust and the torque provided by the tail rotor, in order to understand the influence of these parameters on the frequency drop. Because what we expect to see is the frequency to be reduced due to the presence of damage, while the amplitude will be increased. So this is the database approach. Is I guess the most common industry, and it's because they they just mount many sensors on the fleet and they acquire data, and then based on feature extraction, they can process those signals and specify some threshold and some warning messages to the crew. Will be then indicated in case of having a damage. This is a very nice way to use data for structural health monitoring purposes, but it's difficult to actually have insight of what type of damage is happening right now, or what is the location of the damage and what's the severity maybe. So we need some models, some representative models, in order somehow to correlate the sensor readings with the type of damage we are having. So in order to understand what we are actually seeing, what we are reading right now. So those models might be like in real time automatically update by after feeding them with data. In this case, basically we are talking about digital twins, or they might be numerical models such as finite element models used offline in order to create a readily available database ready to be exploited by algorithms. So it may be a database approach or model-based approach, or a combination of those two approaches. But in the end, we will exploit this data by implementing algorithms in order to get some estimations about the state of the structure. And one of the best ways would be also in a probabilistic way. So a few more words about the models. We have a representative model of the transmission of the tail transmission line. Okay, so starting from the edging, the horizontal shaft, intermediate gearbox, oblique shaft, and then tail gearbox. So we don't have, for example, the tail rotor. Tail rotor is simulated as a couple of thrust and torque provided to the model as an extra input. The purpose, of course, is to calibrate the model in order to start running multiple simulations and create the database. Another input to the model is, of course, the rotational speed at this left side. And we are updating the accelerations from like visual sensors mounted on the cases of the gearboxes. The components inside this gearbox are quite complex. So like a really basic post-processing of the CAD parts was performed, like removing, for example, the teeth of the gear and removing some features in order to simplify the part. But some questions regarding how good some other parameters have been modeled, like the boundary conditions. In this case, the case of the gearbox is just fixed to ground, but in reality is fixed to the tail frame of the tail boom, so which might experience some bending loads, so it might not be a good assumption. Then the bearings might be, in this case, they are simulated as rigid constraints, which is actually not true, of course. Thrust and torque are some profiles. There are inputs as profiles, as curves. So again, we are not sure how realistic is that consumption, and so on. But the most huge challenge is basically to simplify that model and make it run in the time we wish to have, because the target is to create a digital twin, so it must be fast. And we have used the Greg Patton substructure module because the model was built in Abacus. Forgot to mention that before. So we are using this automatic way to simplify this large-scale high-fidelity model, and of course reduce the computational complexity. However, we have done this for all the 23 components and parts of the model, and we ran it a second time to check how much it has been improved, and it needs like 2.5 days. So not really a great improvement. So we have to further reduce our model, and we have to apply some techniques, some more sophisticated techniques in order to perform finite element model reduction. This is a domain that I'm not really familiar with. So anyone interested in having the will to work with that model, I will be more than happy. Now, we have talked about the model in the health and pristine condition, nothing about damages until now. We have to perform the ballistic simulation, and that means fracture analysis. The fracture analysis has been done in the LS-DYNA environment for different parameters, ballistic parameters, such as velocity of the bullet and incident angle in respect with the shaft. And later, after the fracture analysis, dynamic analysis was also performed in order to understand how the frequency response of the shaft has changed due to the presence of the damage. As soon as this shaft, the model of the damaged shaft has been created, we move it and we substitute the healthy shaft with the damaged one in the bigger model of the transmission line. Before doing that, though, we perform model analysis in order to understand how much reduction we are expecting for at least the first 3 eigenfrequencies. And for different boundary conditions, clamped or pinned, we compare the undamaged substructure and the damaged one. And we can see that at least for the first natural frequency, we expect a drop of 13%. As I said before, we are testing various damage conditions. So we call it like damage extent, because like in this case, the damage severity is the greatest, while here it's less, obviously. Then we substitute the shaft with the damaged one, and we run a dynamic analysis. We obtain the signal, the acceleration signal from the IGB, which means intermediate gearbox. It's the one connecting the horizontal shaft with the oblique shaft. For the undamaged and damaged condition, we simply perform a FFT of this signal, and we are trying to find that frequency component that corresponds to the first natural frequency for each phase. As you can imagine, if I compare the same method, if I apply the same method for the signals coming from this experimental setup, the differences are quite high, which immediately means that I have to calibrate my model, go back and check all the assumptions I have already made, and potentially perform model updating. Model updating could be achieved by using algorithms such as MCMC or other methods that I'm currently trying to learn and see what is the best option to apply for this problem. Meanwhile, we are switching to a less complicated model, more easy to manage, and a more accessible, I would say, also test rig, because it's like in the first floor of the building I'm working, so it's really easy. What I have done here is basically I have took the oblique shaft along with the joints and the titanium couplings fixed on these two sides. And I have connected the motor in the left side and the brake with a fan on the right side in order to apply a resistive torque. We have planned the shooting. The shooting is arranged on this September actually, so in 2 months, more or less, we will move this structure to a subcontractor who will use this gun, like the one, to shoot it. Accelerometers will be mounted on the 4 supports over here. So we have 1, 2, 3, and 4 supports, on top of which we have axial accelerometers, monoaxial in 3 supports and biaxial in the second support over here. All right. So I have here a video, a short one, and which actually shows like how the system is controlled, and I have like the lab view window over here showing like how I control the system. If you want me to just try to make it play. This is my colleague. It's actually he switched on the system. What we do is actually we apply through LabVIEW and input speed already predefined. We switch on the sensors we want to read on the column, previously right. We had some values here. We set the target RPM that we want to achieve. It's, in that case, would be like 3,300 RPM. You can see the curve on the bottom and some readings like the current from the inventor, the voltage, and some other readings for control purposes. We reduce the velocity. The sound used to be nice because you could hear like the roller goes really high. Yeah, yeah. And we switch off basically the system, and in the end we have the readings from the sensors. Okay. So an example of those readings from the accelerometers, the FFT of those signals, 1, 2, 3, and 4. Again, we follow the same method. We basically try to identify a peak close to the first natural frequency of the system. And if we substitute the shaft with its damaged version, we aspire to see like this peak moving towards lower frequencies, but the amplitude becoming high. In that case, it is nice with this experimental setup because we will acquire before, during, and after the ballistic impact occurrence. We have, of course, the model of this simplified, as we call it, test tree. Here we have some details of the bearings houses, or in other words, the supports on top of which the accelerometers are mounted. Here we cannot see the accelerometers, but we can see the support of the accelerometer. We obtain some signals, some data from the numerical model. In the healthy case, the damaged condition 1 and damaged condition 2. Damaged condition 2 is more severe than the first one. And in order to understand what if the extent and the location, how does it affect the frequency response of the system. And we can see that we have a decrease of 14% due to the presence of dams. But again, model updating is really significant because we understand that there are significant variations between the data obtained from the experimental test tree and the data from the model. A multi-body, a simplified basically model has been created as well for this rotor. Here it's actually like a beam, like a rotating shaft, where the damage is simulated as reduction of the cross section area. And what we get is the response at each node in the healthy and in the damaged condition as well. So this model is like a very simplified version of the actual system, but it provides us fast and easy to handle data in order to start working with algorithms and try to understand easily what we need to do in the large and actual models of this transmission line. Back to the problem, because we might forget what the problem is, what the target is after so many experimental tests. So we have like different impact scenarios, and this is parameterized according in respect with the location. So the impact is happening in the middle of the shaft or closer to the boundary conditions to the supports, and in respect with the extent of the damage, so the severity. According to these two parameters, the properties of the system will change. So the mass, stiffness, and damping matrices will change due to damage. These chains can be identified by processing the acceleration signals and potentially some features coming from this signal. These features could be the amplitude and the frequency of the peak corresponding to the natural frequency of the system, or for example, in time domain, it could be kurtosis or peak-to-peak, and so on. It actually depends which method provides us the most robust and accurate results. But in the end, what we want to see is, first of all, if we have like a pristine condition or the shaft is damaged, so a binary variable 0, 1. We would like to know the location of the damage and potentially the severity. So quantification, localization, and potentially damage progression are some really ambitious targets of the project and my research. Regarding the ballistic impact monitoring system, it would be nice if we could use machine learning in order to perform monitoring. So what we aspire to do is, based on some specific inputs, such as time, we could use a neural network in order to try to feed acceleration data coming from the sensors, and in the end have the state of the structure formulated and estimated. During this training process, physical laws could be applied in loss function or in other stage of the system. It could be like in the first hidden layer, on the last hidden output layer, and so on. But basically, the thing is that we are trying to feed acceleration. Now the structural assessment of the system could be like an additional step using this estimated and predicted, reconstructed, I would say, acceleration signal. We could use data, a numerical database already defined and created offline in order to avoid calling the model in real time, unless, of course, the model is able to perform actually in real time. So surrogate models could be implemented in that way, so to have a neural network able to work online, but not calling the numerical model several times, as we will waste great computation time. Another way is like the subspace system identification. So while in the first case we were looking at the frequency domain mostly, so how the eigenfrequencies change. Here we are looking how the system parameters change. So if we use the state space formulation and we want to learn about mass stiffness and damping matrices, how these parameters change due to the mass loss and the stiffness reduction after the ballistic impact occurs. So all in all, the target of this research of the proposed algorithm would be to, first of all, utilize the knowledge of physical models, build a system able to work for nonlinear systems, build a model able to work for nonlinear systems, develop a diagnostic algorithm with lesser computational complexity, increase control due to the presence of physics, increased explainability and interpretability, and of course, try to use as less as training data as possible. So at this point, I think I have concluded. So I'm free for questions.